Previous week we had seen some cases of application of differentiation both as a rate measurement tool in physics problems as well as application of differentiation to analyze a function. And specifically talking about analysis of functions, we had seen how differentiation, the value of the derivative being positive or negative, which means the slope of the tangent being positive or negative, indicates whether the function has an increasing nature with respect to x or it has a decreasing nature with respect to x. So we will continue ahead in the discussion of that part today, the application of differentiation in analysis of functions. And as we complete that analysis portion, we will move ahead to integration gradually. Yeah, we will discuss the doubts in the last assignment also, chain rule, etc. Okay. So I will come to discussion of the doubts also. Don't worry. Okay. So before getting back to analysis of functions by differentiation, I want to discuss some examples of application of chain rule. In particular, I want to look at a type of question specifically which I had given you in the revision question bank which I had sent, though I had not tested that in the test, in the major test actually, and that is about differentiation of inverse trigonometric functions. So let us look at that first. So let's understand what are inverse trigonometric functions, and then we will see how to use chain rule to differentiate an inverse trigonometric function. So for example, if we express the relation between x and y as this symbol. Now, this is a little confusing because the symbol, if you interpret it as power minus 1, it does not give you the correct definition. It is not 1 by tan x. Okay. This is read as tan inverse of x. Okay. And what it implies is that tan y is equal to x. Okay. So for example, if we say x is, let's say 1, implies y is tan inverse of 1. So that means tan y is equal to 1, which means that y is equal to pi by 4 or 45 degrees. Okay. So once you understand the definition this way, it's pretty clear, pretty easy to work out the values. Okay. Now, the only thing you have to take care of here is that since we are talking about functions and y is a dependent variable, so it should give a unique value of y, which means we take only the primary solution. Trigonometrically speaking, you know that tan y is equal to 1 will give you multiple solutions. It will give you pi by 4 and 5 pi by 4, and then repeated multiples of that. So the general solution of this will be 2n pi plus pi by 4 and 2n plus 1 pi plus pi by 4. But the primary solution is pi by 4. And in the case of function, remember, it is not allowed that for a value of x, we should have multiple values of y. For a given value of x, there should be only a unique value of y, which means only the primary solution is considered. So that is one thing to understand over here, that trigonometrically, tan y equal to 1 implies that y is equal to 2n pi plus pi by 4 or 2n plus 1 pi plus pi by 4. General solution. Okay. But for y equal to tan inverse x, where y is expressed as a function of x, if x is equal to 1, then y will be considered to be only pi by 4. That is only the primary solution and not the general solution, because a function by definition gives a unique value of y for any value of x. Okay, so that is just one key point to understand. The difference between writing a trigonometric equation that y is equal to or tan y is equal to 1, which has multiple solutions, or writing specifically a function y equal to tan inverse x and x equal to 1, which will give us only the primary solution, because by definition a function must give us unique values. Okay, so hope this point is clear to all of you, and just make a note of this. Now let's just look at some more examples. Okay. So solve for y. So just make a note of this section first. The understanding of trigonometric functions, and I mean inverse trigonometric functions, and then work out these 3 examples and send me the answers on the text message. We'll continue forward from here. Yes, correct Bhavika, correct Kirti. Ryan correct, very good. Akmal correct. Akmal, check the second one. Yes, Bhavika correct for the second one. But first one, Bhavika, you made some mistake, I think. Just check once. So y is equal to sine inverse x. Okay. So for x equal to 0.5, y equals to sine inverse of 0.5, which further implies that sine y is equal to 0.5 or half. So this means that the primary solution is pi by 6 for 30 degrees. Okay. As a trigonometric equation, if y is equal to, or sine y is equal to 0.5, y is equal to 2n pi plus pi by 6, or sorry, pi by 3. No, I was saying correct only. Plus pi by 6, or 2n plus 1 pi minus pi by 6. Okay, this is the general solution. But here this is a function. So for the function, we will take the primary solution. Similarly, the second one, y is equal to cos inverse of x, and we have taken x as 0.8. So cos y is equal to x, or 0.8, or 4 by 5. So that means y is equal to 53 degrees. No, y is equal to 37 degrees. Okay. Or this much in radians. So I'm sure with vectors you must have got familiar with this type of triangle. The right angle triangle with sides 3-4-5 ratio.
Yes, sir.
So the easy way to remember this is that obviously 3-4-5 are a Pythagorean triplet, so it's a right angle triangle. But the smaller side will have the smaller angle. So this angle is 37. Opposite the larger side, there will be the larger of the two angles. So this is 53. And once you remember this triangle, it's very easy to remember these kind of solutions. So from this triangle, you can easily see that sine 37 is the same thing as cos 53, same thing as 4 by 5. Whereas sine 53, sorry, is the same thing as 3 by 5. Whereas sine 53 is the same thing as cos 37, is the same thing as 4 by 5. Similarly, tan 37 is the same as cot 53, is the same thing as 3 by 5. So
Sir,
for various things in physics, it's important to be very familiar with the 3-4-5 right angle triangle.
sir,
What I mean by saying 3x, 4x, and 5x is that the sides are of ratio 3:4:5. So for example, the sides could be, they could be 150, 200, and 250, or they could be 12, 16, 20. But the ratio of the sides, the proportionality is 3:4:5. Then such a triangle will always be right angle, and the trigonometric ratios for the other acute angles, namely 37 and 53, will be according. And the third part, in fact, also is coming from that same triangle, cot inverse of x. If we taken x as 0.75, so that means cot y is equal to x. It's 0.75, which is the same thing as 3 by 4. So that means the primary solution is that y is equal to, 53. So you can always express the value of y in either degrees or radians, whichever is required according to the situation. Yeah, my mistake. It's 3 by 4. Thanks for pointing out. Please make a correction if you're noting this down. This is 3 by 4. Good. So people, you have got this correct. Bhavika, Nirudh, Ayush. Okay, so that's about inverse trigonometric functions. Now, you should also understand that, if I want to write an equation where I want to express A as 1 upon sine A, sine B, let's say, then I should write it as A is equal to, if I'm writing it as a power, I should write it like this. Okay, I should not write it as sine to the power minus 1, because then that means, okay, that it is sine inverse. Whereas if I write C is equal to sine inverse of D, so as you know, that now means that sine C is equal to D, and not that C is equal to 1 upon sine D. If I want this, then I should write C as sine D whole to the power minus 1. Okay, so that's just about symbols and nomenclature. Now let's come to the main important part for us. How do we differentiate inverse trigonometric functions? So one method is to use the chain rule, and that is what we'll be using at the basic calculus level for us. Okay, so differentiation of inverse trigonometric functions by chain rule method. So for example, let's again start with tan inverse x, and I want to find dy by dx. So what I'll do in this example now is that first of all, I'll start with y equal to tan inverse x, means that tan y is equal to x. And now I'll differentiate both sides with respect to x. So differentiation of left hand side with respect to x is equal to differentiation of right hand side. Now in the left hand side, you can see tan y is a function of y, and I'm differentiating it with respect to x. So that is where the application of chain rule will come in. So I'll apply a chain rule step that differentiation of something with respect to x can be written as differentiation of the same thing with respect to y, because it's a function of y, multiplied by dy by dx. So it's really like I'm treating tan y like a z. So dz by dx is equal to dz by dy into dy by dx, like that. Okay. So and the right hand side is obviously unity, because differentiation of x is 1. And then we proceed with the normal formula. You know that differentiation of tan is sec square. So this becomes sec square y into dy by dx is equal to 1. So far everything is smooth. Dy by dx is equal to 1 upon sec square y. But so it's fine. We have completed the differentiation. But typically we want to express the derivative in terms of x and not in terms of y. So I should additionally make use of the identity that sec square theta is equal to 1 plus tan square theta for all theta. Okay. So substituting that over here, I can say that dy by dx is equal to 1 upon 1 plus tan square y. And the advantage of doing that now is that I have taken tan y as x. So I'll substitute this over here now. And final step, I'll get that dy by dx is, in terms of x, it is coming out to be 1 plus x square. Okay. Now, if you look at a advanced calculus book in mathematics, you'll see that this is a direct formula given. Okay, but I don't want to confuse you with a whole lot of direct formula which you have to memorize. So at our level in basic calculus, which we require for physics, if we have come across an inverse trigonometric functions, then instead of memorizing a whole set of formulae for various inverse trigonometric functions separately, we will use the chain rule method, and we'll use our existing knowledge of differentiation, chain rule, and trigonometry to come up with the steps required to show that this is this. Okay, so just review the steps in this, make a note of any of the critical steps that you want to, or the whole thing.
So
We'll discuss some more examples. Yes, Beta.
I did not understand the tan y differentiation part. I mean, like, why didn't we just write it as sec square y? Why did we again? I mean, why did we apply the chain rule here?
Because see, what is happening now, we are differentiating. See the step before that, we are doing differentiation with respect to x of what? Tan y. Okay. Now, what is the formula that we know? We know that differentiation of tan x with respect to the x is sec square x. Now, this is the formula we know.
Yes, sir.
But we cannot directly differentiate a function of y with respect to x. No? So it's like,
Okay, sir.
got the
Understood.
thing now? So we are treating this whole thing like a function of y now. So
Okay,
that is
sir.
your chain rule. So differentiation of a function of some other variable with respect to x will by chain rule become what? Differentiation with respect to y of that function into dy by dx. Understood now? Beta?
Yes, sir. Understood.
So next step, this becomes f prime of y into dy by dx. Now that f prime is f prime of which function? Tan function. So it becomes x square. So it's here becoming sec square y into dy by dx. So that is how we are making use of the chain rule to get past this issue that we had this bracket has a function of y, but we are differentiating with respect to x. So how do we deal with that chain rule?
Okay, sir.
Like another example of this, you've seen, like, we had, suppose volume was a function of radius, and we wanted to find out rate of change of volume with respect to time. So that would become rate of change of volume with respect to radius into dr by dt.
Yes,
So
sir.
that's the same kind of thing how we are using in rate measuring problems, chain rule, like that we are using here also.
Understood.
Okay, so let's look at another example of differentiation of an inverse trigonometric function. So this one is for you people to try out. So now it is given that y is sine inverse of 3x. Okay. In fact, let's just make it 3x, not 3x plus 2. So first thing is find dy by dx. Okay. And for this function, and find the value of the derivative at x equal to 1 by 6. Just try this question out, people. Okay, Avanti, I will scroll up. Yeah, right. Let's get back to the question. Yes, so I'm getting the answers. Let me check. Akmal, yes, very good. That's correct. Yash, very good. That's correct. Bhavika, to answer your question, dy by dx will not be equal to 1 unless we say y is equal to x. Yes, definitely. The only unique function, actually, y is equal to x plus any constant. So dy by dx is equal to 1 for, you can say, a family of functions which are of the type. So dy by dx is equal to 1 means y is equal to x plus any constant. It could be x plus 1, it could be x, it could be x minus 1, like this. Because the
Okay,
differentiation of a constant is 0, as you know.
okay, sir. So that is why we didn't do anything to dy by dx in the previous question, right? We just kept it like that because we didn't know that y was equal to something.
Sorry, come again, beta. In which thing we did?
Sir, in the previous question, where we
Ah,
were applying the chain rule for differentiating tan y, we wrote sec square y into dy by dx. So we did
ah,
not do anything to dy by dx because we didn't know what y actually is, right?
exactly. But we know y is sine tan inverse x, but we didn't know how to directly write dy by dx. Na? So we
Okay.
had to use the chain rule, and then we got the relation that okay, dy by dx into sec square y is equal to 1, right?
Okay, sir.
So then we interpreted that fine dy by dx is 1 upon sec square y, which we can therefore write as 1 upon 1 plus x square. So
Yes,
similar
sir.
kind of thing we'll do over here now. Okay, so we don't know the direct formula for differentiation of sine inverse. So instead of differentiating dy by dx as differentiation of the right hand side directly, first we will interpret the function. So we'll interpret the function in this way, that y is equal to sine inverse of 3x. This means that sine of y is equal to 3x. Okay. Now this relation we can differentiate because we know the differentiation of sine function, and obviously we know the differentiation of a linear function which is on the right hand side. So this is easier for us to differentiate than this thing because we didn't have any formula for differentiation of sine inverse function, right? So next thing, same approach, we differentiate left and right hand side with respect to x. So now chain rule. So cos y dy by dx is equal to 3. So that means we can write dy by dx or the rate of change as 3 upon cos y. Now the same problem, I want to reduce this in terms of x, and 3x is defined as sine y. So what I should do, I should first express cos y in terms of sine y. So it is square root of 1 minus sine square y. Then I should express sine y as 3x. So it becomes this. So now substituting this, see that dy by dx is becoming 3 upon square root of 1 minus 9x square. So this is the answer to the first part. The derivative of the function is equal to this value, 3 upon 1 minus 9x square. Now we want to find the value of the derivative, that is the value of this expression for x equal to 1 by 6. Okay. So just substitute x equal to 1 by 6 in that, and you'll get a numerical value of the derivative. So that will be the slope of the tangent at the point x equal to 1 by 6.
So can you please explain what did you after the third step?
After which step it is?
The third step.
Differentiation of sin y is cos y, no?
After that,
So after that, we have just transferred cos y to the other side. So dy by dx is 3 upon cos y. And then we've used the identity that sine square plus cos square is equal to 1. So cos can be expressed as square root of 1 minus sine square, right?
yes, sir.
Okay, so now the second part, we want to find out the value of the derivative at x equal to 1 by 6. So that is nothing but dy by dx at the specific value of 1 by 6. So that will become square root of, 3 upon square root of 1 minus 9 into 1 by 6 square. Two root 3. Okay. So this becomes this much. Very good. So Anirudh, was
No,
this
sir,
correct?
I gave it wrong. Sorry, I got the
Yeah.
answer.
But you understood that now.
Yes, I got it.
On its own, it is correct that dy by dx can be expressed upon 3 upon cos y. So it is 3 upon 3 sec y. But then sec y has to be converted into the form of x. So you could help. Your answer is correct. Kirti correct. Freya correct. Okay, so next we will move on into some more applications of differentiation, but in terms of analysis of function. So going back a little to what we had seen in the last lecture, Okay, so let us go back to analysis of functions by application of differentiation or application of derivative. So in this concern, one of the things that we've already learned is that for a given function, if f prime x or dy by dx is positive for a certain interval, then it implies that the function itself is increasing for the given interval. And similarly, if derivative of the function is decreasing in a certain interval, then the function is, sorry, derivative is negative, that means the function is decreasing for that same interval. Okay. Now we will take this analysis a little bit further today. Okay. And we will understand the concept of maxima and minima. So this is one thing we've already seen before. Now the next thing we'll see is maxima and minima of a function. And in order to define maxima and minima, first we need to understand two more terms. We need to understand the concept of domain and range of a function. So domain of a function, so let's say the function is y is equal to fx. So domain is defined as the set of values of x. Okay, that is the independent variable. Okay. And the range of the function becomes the set of values of y or the dependent variable, okay, for the corresponding domain. Okay, so to understand this, let us look at one more point, that domain of a function may be its natural domain, that is all values of x for which y is a real value. Okay. So that is the natural domain of a function. I'll explain this with examples also. Or on the other hand, it may also be a restricted domain. And this typically happens because of any specific situation to which we are applying the situation. Any specific situation to which the function is being applied. So make a short note of this if required. Okay. And I'll just explain this concept of restricted domain versus natural domain with a couple of examples. It will be very easy to understand. It's just a simple term that we need to understand. So of course, this part, we have seen examples of this application before also. And we are going to see that again with some more examples today. That the behavior of a function, this is what we had called the behavior of the function last time. Behavior of a function in terms of whether the function is increasing or decreasing in a certain interval. So how do we understand that behavior? By looking at the algebraic sign of the derivative. If the derivative is positive in a certain interval of x, that means in that interval, the function has the increasing behavior. If it is negative, it has the decreasing behavior. Now, ahead of this analysis that we can see the behavior of the function, we're going to look at something else today, which is maxima and minima. And to understand maxima and minima, first of all, we need to understand these two new terms, domain and range. So in terms of definition, this is what domain is. It is the set of values of x or whatever the independent variable of the function is. And range is the set of values of y. That is whatever the dependent variables is.
So can you please explain restricted domain once again?
Yeah, I'll explain with an example. Just note down the definition first. Okay.
Yes.
So if we apply any artificial restriction on the domain, that I want to take only certain values of x because I'm applying it to a certain situation, then we say that we have taken a restricted domain. Whereas if I'm taking all possible values of x for which y is defined as a real number, then that means I'm taking the natural domain of the function.
Okay, sir.
So the moment I give you a couple of examples, you'll understand what this means. It's just like a very simple thing. Okay, so let's look at the concept of domain and range with a couple of examples. So for example, if I have the function y is equal to x square, then we can see that the natural domain is that x belongs to the set of all real numbers. Okay. Because what is the natural domain? It is basically the set of values of x for which y is real. Okay. So there is no number x which will give you a non-real value of y, or for which y cannot be defined. So the natural domain of this is this. Okay. So now we can see, so therefore for this natural domain, okay, the range of the function is that y is equal to, y belongs to the set of all non-negative numbers. Okay. Because you know that that's how the graph of the function looks. Even though we cannot draw the complete graph because we're talking about x taking all real values. So we cannot draw a number line that includes plus and minus infinity. But we can imagine that, okay, if x is going over the entire number line, then y is going over the entire part of the number line, which is in the non-negative region. So we know the graph looks like this. But for no value of x, does y take a negative value? So the range of the function is not all real numbers. The range of the function is less than all real numbers. It is only non-negative real numbers. That is because that is the nature of the function. Whereas had the function been something else, like had the function been y is equal to x cube, you can see that this has again a natural domain of all real numbers. But this also has a range of all real numbers because this has a different shape, the graph. Now you might at this stage say that, okay, if I don't know the graph of a function, then there's no way I can get the range of a function. And to a certain extent that is true, but we will see how calculus helps in this regard also. Okay. So these are two examples where I'm seeing the natural domain of a function and accordingly I'm calculating the range for the given natural domain. We will come to restricted domains in a moment. Okay, but let's take these two examples of natural domains first. For example, if I have the function y is equal to 1 by x, then you can see that the natural domain is not all real numbers. The natural domain is now minus infinity to 0, but not including 0, union with 0 to infinity. Because at x equal to 0, y is undefined. It is not a real number. It is not infinity. It is undefined simply. So this one has a natural domain, which is not all real numbers. Okay, it is the set of all real numbers excluding one particular number, which is 0. Similarly, here the range will become that y again belongs to the same thing. All real numbers other than 0. Because no matter what value of x you can take, y will never become exactly equal to 0. As x tends to infinity, y tends to 0. But y is not exactly equal to 0 for any particular value of x. So both the domain and range are actually interestingly same in this question. Okay, so let's take a couple of more examples. So next example, y is equal to 1 by x square. So what is the natural domain? And what is the corresponding range? And another example we take is very interesting one. Y is equal to, let's say, square root of 16 minus x square. So what is the natural domain of this function? And what is the range? So don't worry about restricted domain yet. We'll discuss about that. First, let's get a grip on what is natural domain of a function, how to analyze that. and from that how to analyze the range of the function for simple types of functions like this. Okay. As we come to more complicated functions, we'll see that calculus becomes necessary to analyze. Archit, you have to be careful, beta. Remember, 1 by 0 is an undefined operation, right? 1 by 0 is undefined operation, Archit. Okay, so try it again. Yes, very good. Health, your answer is correct. Okay. Akmal, your answer is correct. Very good. Archit, your answer is correct now. Very good. Anirudh, just go over the logic again. See, there is no problem. For example, if I take x as 10, okay, 1 upon 10 square is a defined number. No? It's 1 by 100 or 0.01. Or for that matter, if I take Kirti, correct?
So is there something wrong with the answer?
Anirudh, yeah. See, the thing is, your domain does not include the points like 10 or -5 or something like that. No? Whereas the given function, the first part, you can see that if you take x as 10 or -5 or -2 or even 1000 or whatever, y is defined. No?
Sir, I've
So,
sent the natural domain for one as x belongs to -infinity to 0, union of 0 to infinity.
okay, that is correct. I think there are two enabled, so I'm confusing.
Okay.
Wait, let me check. What is your full name, beta?
Anirudh Prakash, should I rename it?
Sorry?
Should I rename it? It'll be easier for you identify.
No, I can see only one Anirudh. So the message I've received from you is that, just a minute. Yeah, Anirudh, what is the message you sent? Can you just read out?
For one, the natural domain is x belongs to -infinity to 0, union of 0 to
Okay.
infinity.
Whereas the message I have received is that is -1 to 0. So maybe some software issue. Okay.
That is I, not -1. Actually, I have
Oh,
written it.
okay. Acha. It's like you have written infinity as I. Okay. Yeah, that's correct.
Yeah.
Good. Okay. So the domain actually of 1 by x square, the natural domain is the same as the natural domain of 1 by x. But the range is the thing that is becoming different. You know, because we have x square in the denominator instead of x. So now you can see that. So these things are, more like they're matters of observation in maths and no specific method as such, apart from, following the general principle of algebra that division by 0 is an illegal operation. Yeah, apart from that, there's no real specific concept that we are using. Okay. So anyway, so you can see that natural domain. So in that, the only principle we have to apply that the denominator should be non-zero. That means x square should not be equal to 0. So that means x should not be equal to 0. So that is the only restriction we have on the domain. So accordingly, the natural domain is that x belongs to the set of all real numbers apart from 0. So restricted to this. Okay. Now we can also express this in another way. We can also write it like this, that x belongs to the set of all real numbers excluding. So excluding is written with a minus sign, and a single number we want to exclude. So we'll write it in curly brackets. So this notation here basically means the same thing as this. And of course, we can also write it like this, that x is greater than minus infinity less than 0, union with greater than 0 less than infinity. So all these three statements mean one and the same thing basically. Okay. Now the difference is when we are looking at the range, we can see that now the range cannot have positive values, okay, and it cannot be 0. Sorry, the range cannot have negative values because x square is always non-negative, and it cannot have a value of 0 also because it is 1 upon some number. So there's no number which will give you that value that y is equal to 0 over here. So the range is actually in effect all positive numbers. So y belongs to the set of all positive numbers now, 0 to infinity. And yes, you have all got this correct, those who have sent the answers. Okay, very good, Health. Your answer for the second part is correct. Excellent. Okay, Bhavika, correct. Very good. Anirudh, correct. Akmal, correct. Very good. Okay, so this second question, we are using a different concept now. The concept that we'll use algebraically in the second question is that square root of a negative number is undefined. Okay, so y is equal to square root of some expression, that is 16 minus x square. So that expression 16 minus x square should not become negative. So effectively, we have to solve an inequality that 16 minus x square should be greater than equal to 0. It will include 0. Okay. So the natural domain will come from the solution of that inequality. So for inequality, you have number of ways. The wavy curve method is the easiest one, like we discussed before. So as I said, again, it's a matter of observation and a bit of algebra. So y is defined as square root of some quantity. So the general algebra principle here is that square root of a is not a real number if a is negative. So this becomes a restriction. So that means over here, for y to be real, 16 minus x square should be greater than equal to 0. Or 4 minus x into 4 plus x should be greater than equal to 0. So that means x should be between minus 4 and 4. Or we can say that the natural domain is minus 4 to 4 closed interval. Okay. So the easiest way to interpret this is, or easiest way to analyze this is by the number line method that we discussed before. Okay. So if you consider the set of all real numbers x, now the two factors that we are multiplying, 4 minus x and 4 plus x, the critical points for them are minus 4 and 4 respectively. So if you look at the quantity 4 minus x, it is negative for values less than 4, and it is positive for values less than 4, and it becomes negative for values of x greater than 4, and it's exactly equal to 0 at this point. And the second factor that we have, which is 4 plus x, for that the critical point is -4, because as long as x is less than -4, it will be negative. At this point, it will be 0. And as long as x is greater than 4, it will be positive. So now when we look at the product of these two, 4 minus x into 4 plus x, we can see that the product is behaving like this. It is negative here, positive here, again negative here, and 0 at this point and 0 at this point. So we'll include these 2 points because we are solving for greater than equal to 0. So the natural domain becomes this. This is the set of values of x, all values of x possible for which y is real. So now let's talk about the range. Now the range is going to be very interesting for us here. Now let me check your answers for the range also. Many of you have sent the correct answer. Yeah, very good. I think all of you have sent the answer for range. You got it correct. Health, your answer is correct. Akmal, your answer is correct. Bhavika, your answer is correct. Very good. Okay, so let me explain the range again for everybody. So our function is square root of 16 minus x square. Now you can see that the quantity 16 minus x square. In this, what is happening? This is its minimum value equals to 0. And that is for x equal to either plus or minus of 4. Whereas its maximum value is 16, and that is for x equal to 0. Okay. So therefore, square root of 16 minus x square, it will have a maximum value of square root of 16, which is 4. Okay. And it will have a minimum value of square root of 0, which is 0. So that is showing me that my range is such that y cannot come less than 0 and cannot exceed 4, or that y belongs to the closed interval 0 to 4, which is shown with box bracket. So this is the range for its natural domain. So you can see that, just by applying simple mathematical logic, we are able to get by in questions like this. Okay. But there is going to come a time when we'll come across some functions where we are not going to be able to get by so easily. Okay, so I'm going to show you an example of 2 of that. But before that, let's talk about restricted domain also. So people, I hope these examples are clear to all of you. So actually this is, more of maths than anything else. So this kind of analysis and logic will also immensely help you in maths later, because calculus actually is a very big portion of your maths syllabus. But of course, there are many more things in advanced calculus that you will learn in mathematics when you come to that, compared to what you're learning here in basic calculus for physics. So this is going to have a dual benefit. Not only it is going to help us in physics, you can think of vectors and calculus like a toolbox. It's a toolbox that unlocks problem solving for us in physics. Whichever chapter of physics we look at in the future, whether it is current electricity or magnetism or Newton's laws of motion and mechanics, okay, or anything like that, heat and thermodynamics, to analyze physics more closely, we need more mathematical tools. And the very important components of our toolbox are going to be basic calculus and vector analysis. Okay. So now let's talk about restricted domain. So restricted domain is a situation where the domain of a function is taken as some subset of its natural domain, okay, because of some external factors. Okay. So the domain of a certain function may be specified, okay, as a subset of its natural domain. Due to some restrictions imposed on the physical quantities represented by the independent variable. There's a very simple example of this. Let's see. Suppose I have a motion related problem. Okay, so I have motion along a straight line such that velocity v in meters per second varies with time t in seconds, as let's say v is equal to 5 plus 2t. Okay, and the motion starts at t equal to 0 and ends at t equal to, let's say, 5 seconds. So the moment I'm doing this, you can see that this is now a physical restriction. Okay. So what is happening is v is equal to 5 plus 2t. This we are interpreting as v is some kind of function of t. So time t is the independent variable. Okay. And v is the speed, v is the dependent variable. Okay. However, in this function, because there is a specification on time from the situation we are applying it to, which is basically that the motion lasts only from 0 to 5 seconds. It means that we have started our stopwatch when the motion started. So for us, negative time doesn't make any sense. Okay. Suppose the motion started and we started the stopwatch only 2 seconds later, then we could have said that, okay, the motion actually started at t equal to -2. So in such a situation, negative time might make sense. But here we are clearly, the question itself or the situation given to us is specifying that we have started the measurement of time in our experiment, the motion, the moment the motion starts. Because it's given to us that the motion starts at t equal to 0. So our clock is synchronized in that way, that we are starting our clock or our stopwatch the moment the motion starts, and we are stopping at the moment the motion ends. So that means we are having the independent variable with a restricted domain. And the restriction is because it is imposed by the physical restriction, not because of some mathematical restriction. The natural domain of this function would have been minus to plus infinity. So this is an example of a restricted domain. Okay. If we had the function, if we had the maths function y is equal to 5 plus 2x, where x and y are just two variables, then we would have seen that the natural domain would have been all real numbers. X is the set of all real numbers, and accordingly the range would have been that y belongs to the set of all real numbers again. That is not y, that is infinity. But here we are going to have a restricted domain. Now the moment we have a restricted domain, therefore what happens? So therefore the range, that is the values of v, will also depend on the restricted domain. Okay, so the range will be for the given domain. So the given value of t is from 0 to 5 seconds. So you can see the value of velocity, it starts from 5. Okay, and by the time your time reaches 5 seconds, it becomes 5 plus 10 or 15. So it ranges between this and this only. So again, the range is also affected by the fact that our domain is restricted. Okay, so this is a perfect example to show you that when we apply functions in some physics problem where the variables are not representing pure numbers, they are now representing some physical quantities, then the particular system to which we are applying it might impose some kind of restriction, some kind of physical restriction. So when that happens, so as far as the maths of that function is concerned, the domain is no longer the natural domain, it is a restricted domain. Okay, so hope this makes this point clear of restricted domain versus natural domain. Yeah, Rohan, you can just send me the question numbers that you have doubt in on the text message, whether it is from the module or from the worksheet or the revision sheet. Just mention the exercise it is from and the question number. I will come to those doubts also. Okay. Now let's also apply in the meantime the concept of restricted domain to one of the questions that we've already done. So for example, let's go back to this interesting one that we had, that square root of 16 minus x square. Now given that x belongs to, let us say, say minus of 2 root 3, okay, to root 7. So it's a bit of an odd thing, but let's say we have that. So x belongs to this. So it's a restricted domain. For whatever reason, it is restricted. Okay. Find the corresponding range. So I'm repeating, x belongs to the interval, the closed interval minus of 2 root 3 to square root of 7 to positive of square root 7. Yes, health, very good. That's correct. Yes, Rohan, I will look at that question. I will work it out for you. Okay. नहीं अकमल बेटा रेंज आप तो डोमेन बता रहे हो ना, रेंज क्या कॉरेस्पॉन्डिंग वैल्यूज ऑफ y है ना. Now you can see that x is taking the values of greater than equal to minus of 2 root 3 and less than equal to root of 7. So now what about x square? X square को क्या हो रहा है, as x goes from minus 2 root 3 to 0, okay, x square goes from 12 to 0. Okay. So corresponding, whereas x goes from 0 to root 7, so x square goes from 0 to 7. So next you look at the quantity 16 minus x square. So 16 minus x square क्या हो रहा है, as x is going from minus 2 root 3 to 0, x square is going like this. So 16 minus x square is going where? 16 minus x square is decreasing from 4 to 0. Okay. So correspondingly, square root of 16 minus x square is going from 2 to 0. Whereas this side of x equal to 0, as x is going from 0 to root 7, x square is going from 0 to 7. So what about 16 minus x square that is going from, it is going from 0 to 9. Okay, so what is happening to square root of 16 minus x square? It is going from 0 to 3. So basically what we can understand is that if you think of the number line x, your 0 is somewhere here, your minus 2 root 3 somewhere here, and your root 7 is somewhere here. So here what is happening to the quantity y, which is square root of 16 minus x square. It had a value of 2 over here. Okay. And is dipping. It's coming to a value of going to a value of 4 minus 2. It is going from 2 to 4. Wait, I've got something wrong here. It is going from 4 to 16. Yeah. So this is going from 2 to 4. So it's actually increasing here. Going to a value of 4. And similarly here, as x square is going from 0 to 7, 16 minus x square is going from where to where? It's going from 16 to 9. So this is going from 4 to 3. So it's coming down here, where at this point, y is equal to 3. At this point, y is equal to 4. And at this point, y is equal to 2. So the function has this kind of behavior, that for x equal to minus 2 root 3, the corresponding value of y is 2. And then the value of y increases. It increases till it reaches x equal to 4. And then in this part, it decreases till it reaches again y equal to 3. So overall, what is happening? Y is going from 2 all the way up to 4, and then coming all the way down to 3 as your x is going from here to. So what is the range? The range is that y belongs to the set from 2 to 4. It's never coming below 2, it's never going above 4. For this restricted domain, it's never coming below 2, it's never going above 4. Okay, so don't worry, Akmal and Bhavika, it's little confusing in the beginning. Okay, we'll get used to this. And this is something in which calculus will also immensely help as we discuss more and more. So now that we have understood the concept of restricted domain and corresponding range, now we come to the concept of maxima and minima. Okay, so I'm just leaving this here for a moment for you to analyze the whole thing. Okay. So now coming to the concept of maxima and minima of a function y is equal to fx. So we'll see that firstly there is something called global maxima and minima. And this is a term which is very easy to understand because it's just as language suggests. Global means basically what? The overall. So global maxima and minima are nothing but the maximum and minimum values of the function's range. So for example, if we have the function y is equal to x square, okay, then it means that the range of the function is, as we saw, 0 to infinity, unless we restrict a domain. Okay, so we can see that the global maxima for this function is that y tends to infinity, and the global minima of this function is that y is equal to 0. Similarly, we had the function y is equal to square root of 4 minus x square. Okay, now we can see that for this the range that is between 0 and 2. Okay, because the largest value of the quantity inside the square root is 4. So y never goes beyond square root of 4, and the smallest value is of course 0. So y never comes below 0. Okay, so we can see that the global maxima is 2 and the global minima is 0. But also let's look at an example of a restricted domain. So suppose I have y is equal to sin x, but x is only between 0 and pi by 6. So this is an example of a restricted domain. Okay. Then we want to find global maxima and minima. So we'll understand that for the given domain, what is the range? So we can see here that this is a restricted domain. And if we visualize the overall graph of the sin x function, we know that the function in general goes like this, where this point is pi by 2 and this value is 1. But here we are taking a restricted domain. We are only going between 0 and pi by 6, which is somewhere here. And at pi by 6, we know the value is half. So you can see that this is our domain now. This is our domain. So correspondingly, this is becoming our range. So for this restricted domain, our range is that y belongs to 0 to 0.5 or half for the given domain, that is restricted to 0 to pi by 6. So therefore, for this domain, the global maxima is 0.5 and the global minima is so I'm just minimizing this a little, just go through the definition of global maxima and minima. It's very simple really, that if the range is known to us, then the upper limit of the range becomes the global maxima and the lower limit of the range becomes nothing but the global minima. So it's pretty simple really. It's all to do with the calculation of the range. So basically, you can also interpret this statement like this, that for y equal to fx, if the range y is A to B, let's say, then A is the global minima and B is the global maximum. So all this means.
Sir,
Yes.
in the second example, sir, x will tend to be 0.
Sorry, x will.
It will not be exactly equal to 0, sir. Root 0 will not be possible.
Why in the second example y equal to 0 will not happen? Because x's value can be taken as 2, no? 2 or plus minus 2.
Sir, minima, sir. I'm talking about minima.
Sorry, come again, beta.
Sir, if we take y equals to okay.
If we take
Sir,
y
but
equal to
y-
square root of 4 minus x square, then what is the natural domain of the function? It is minus 2 to plus 2, including both the points, no?
Yes, sir.
So the moment you included the point x equal to 2 in your domain or x equal to minus 2 in your domain, y is becoming 0, no? Square root of 0 is exactly 0, no? That's why. You understood now?
Okay, sir.
Yeah.
Understood, sir.
Yeah.
Sir,
Okay, so that's about global maxima and minima. Now we have a more interesting term called local maxima and minima, and that is where the analysis of calculus becomes more important. So let's now, the term local maxima and minima itself is a little bit more abstract. So let us understand that by understanding it visually first. So let's say I have some function whose formula is not given to me, but the graph of the function is given to me. And that graph looks something like this. It's in a limited domain, but within that domain, its behavior changes. It goes from increasing to decreasing to again increasing. So this is some kind of a function given y is equal to fx, where the behavior of the function is such that, let's say, it starts from the point x equal to a, increases till it reaches this point b, then the function starts dipping again, or it starts decreasing again, decreases all the way till it reaches the point c, and then again it starts increasing all the way till it reaches the point d. So the corresponding values here are f of a, is similarly f of b, similarly f of c, and so on and so forth. So you can clearly see that the way the function is drawn, you can see that it's having a domain, seems to be a restricted domain of a to b, sorry, a to d, and therefore it's having a range in this case of f of a, whatever that lowest value is, up to f of d. So you can also see that the global maxima, it equals to f of d, and the global minima, that equals to f of a in this particular case. Okay, but now pay attention to the point b, and it has something very interesting here, that what is happening is that the function fx increases from x equal to a to b. Okay, and then the function decreases from b onwards up till c. Okay, so what that is showing us, that the function peaks, it has a temporary peak at x equal to b. So such a peak is called this peak point is called a point of local maxima. Why it is not the same thing as global maximum? Because you can see the value of the function at this peak, it is not the overall maximum. No? There is somewhere else where the value of the function is more than this. So any point beyond here, the value of the function is becoming more, but it's reaching a sort of localized peak. It's increasing, reaching that local peak and then dipping again. So that becomes a significant point for us, because the behavior of the function is changing at that point. So that's why that is called the local maximum. So additionally, what we can see is that the function is such that the derivative of the function at the point x equal to b will be 0, because that is the peak point. So at the peak point, slope of tangent equals to 0, which means that if I draw tangent exactly at the point x equal to b, it should be a flat line. This is the tangent at x equal to b. Similarly, you'll see if I draw tangent exactly at the dip point, that will also have a slope which is 0. This will also have a slope equal to 0. This will also have a slope equal to 0. Okay. So again, you can see it's like an inverse of this behavior as far as the point C is concerned. The function is decreasing from x equal to b to c. And then again, the function is increasing after c. So this is showing us that the function has a dip or like a valley at x equal to c. So such a dip point is called a point of local minima. And what happens is that the derivative of the function at x equal to c is 0. Okay. So this is a second type of maxima and minima we are talking about compared to the global maxima and minima. It is the type of maxima or minima where the function's graph shape has to reach a peak point or it has to reach a dip point. So just make a note of this first. Yeah, Kirti, I will answer your question. If we had taken the restricted domain in such a way that we went only up to the point B, then at the point B, we would get not only the local maximum, but the global maximum also. Okay. So we'll take various such examples where we'll see combination of such things happen.
So if the function, if we assume the function goes ahead and if it dips at D and again increases from, say, decreases from D to A and again increases from E to F.
Uh,
So the local maxima will be at D, right?
yes.
Okay, sir.
Okay, so let's analyze this with an example now. And let's say we take a limited domain from -2 to 2. Okay. So first of all, find the local maxima and local minima. That is, if any, because the function's graph can be such that it simply doesn't have a local maxima or local minima. Analyze the behavior of the function. That is, whether it is increasing or decreasing in the given domain. And from that, find the range and global maxima and minima. Okay. And using all this, we will plot an approximate graph for the function. So let's work out this question and understand this. So what is the tools that we have to do all this? We have the tools that for a given function y equal to fx, if f prime x is equal to 0, so is if the derivative of the function is positive, it means that the function is having the increasing behavior. If f prime x is negative, it means that the function is having a decreasing behavior. And if f prime x is equal to 0 at a point, then it is either local maximum or local minima. But what will happen is at a point of maxima, the function would have increased and then decreased. At a point of minima, the function would have decreased and then increased. So if you do the analysis of the intervals in which the function is increasing and decreasing, you can understand that which sort of point is giving us local maxima and which sort of point is giving us local minima. So let's do that over here. So in this case, the function is 3x minus x cubed plus 2. So the first step is find the derivative of the function. Okay. So that is 3 minus 3x squared, which we can factorize as this. And we can do that number line analysis on this. And we can understand that the derivative of the function f prime x, which is this, has the following properties: that on the number line for the two factors 1 minus x and 1 plus x, the critical points, as you can see, are -1 and 1. So 1 minus x is negative up to 1, becomes positive after that, 0 at 1, and 1 plus x is negative for x less than -1, positive after this. Oh, sorry. Yeah. So you can see that the derivative of the function f prime x, it is positive. Oh, I made a mistake here. This should be reverse of this one. This should be, it's 1 minus x and not x minus 1. So 1 minus x is negative the moment x becomes greater than 1, and positive for values less than. So now as far as the derivative is concerned, the function's derivative is negative in this region, 0 at this point, positive in this region, 0 at this point, 1, and then again negative. So that means as far as the function is concerned, it is decreasing in this region, increasing in this region, and then again decreasing. So the answer to the first part is that at x equal to -1 and x equal to 1, f prime x is equal to 0. Whereas x belonging to -2 to -1, the function is decreasing. X belonging to -1, not including -1. So -1 to 1, the function is increasing. Okay. And x belonging to 1 to, we are taking restricted domains only up to 2, the function is again decreasing. So what this tells us that the shape of the graph of the function is like that, decreasing, then increasing, then decreasing. So obviously it's going to have, the shape of the graph is going to be something like this. It's decreasing, then increasing, then decreasing, like this. Where the critical points, where the slope is 0, are respectively x equal to -1 and x equal to 1. So this is the point where it has a local maximum. And this is the point where it has a local minimum. So from this analysis, we can see that therefore fx has local maxima at x equal to 1, and its value is how much? Y equals to, so you can see 3 minus 1 plus 2, so it's equal to 4, and fx has a local minima at x equal to minus 1, where the value is minus 3 plus 1 plus 2. So that is 0. So at this point, you can see our y coordinate should become 0. And at this point, our y coordinate should become 4. Okay. So effectively, we have done the second part also. We have found out the intervals in which the function is increasing or decreasing. This is our second part. These are the intervals in the function in which the function is decreasing, then increasing, then again decreasing. Or on the number line, you can see the intervals. The function is decreasing in this part, then again increasing in this part, and again decreasing.
So the local minima will be y equal to minus 2, right?
कैसे minus 2 beta? Put the value of x as minus 1 in the function. 3x minus x cube. Okay, let's check this out. F of minus 1
minus 1 is minus 4
is
plus 2.
minus 3, right? Plus 1 plus 2.
Okay,
is,
so I forgot the minus x3 thing.
yeah, okay, there's this term. Let's see.
So
Yeah.
can you explain that previous sum where you gave an example for the restricted domain that y is equal to root of 16 minus x square? I did not understand that range. Sorry, the range part properly there.
The range part, na? Okay. So see what is happening. Yeah, this part, na? Yeah.
Yes.
So यहाँ पे we had taken x as this part of the number line from minus 2 root 3 to root 7. These were our values of x. Okay. So now if you look at the quantity x square, how that is varying. Okay. At this point, x square's value is how much? It is 12.
12.
At this point, x square's value is 0. And at this point, x square's value is 7. Okay. So now let us look at the quantity 16 minus x square. So 16 minus x square यहाँ पे कितना है? 4 है. यहाँ पे 16 है. और यहाँ पे 9 है. Correct?
Yes, sir.
So understanding now what's happening to y. Y is square root of 16 minus x square. So that is 2 over here. Okay. It's 4 over here. And it's 3 over here. So as your x is going from minus 2 root 3 to 0, what is happening? Your x square is actually decreasing from 12 to 0. So 16 minus x square is actually increasing. So y is actually increasing from, so y is going from the value 2 to the value 4 as your x is changing from minus 2 root 3 to 0. Right? And then in the next thing, what is happening? As your x is going from 0 to root 7, x square is increasing. So x square is increasing. What is happening to 16 minus x square? That is decreasing. So what is happening to y? Y is decreasing. So it's decreasing from here, but up to the point y equal to 3 only, because I'm going only up to x equal to root 7. So now you can see what's happening to your y coordinate. It is going from 2 to 4. It's going up first. from 2 to 4 as your x is going from here to here. But the second part, what's happening is coming down from 4 to 3. So overall, your y coordinate never goes beyond 4 and never comes below 2.
Yes, sir.
Understood? No? So it's a little bit complicated, but that's the analysis. Okay.
And so can we find out the local minima and maxima over here?
For that function, yeah, we'll do that also. That square root of 4 minus x square, that function also will do. Okay. But let's come back to this question for a moment. So we'll see that any given function, we can find local maxima minima as well as global maxima minima. Okay. But now coming to this example, what we can make of the graph of this. So we have this whole analysis now, and we have to draw the graph only between -2 and +2. So let's also check out what is the value of y when x is equal to -2. Can you tell me what the value of y is and what the value of y is when x is equal to +2? So you can see that y is equal to 3 into x minus x cube plus 2 now. So this is becoming -6 plus 8 plus 2, right? So it's becoming +4. So here the value should be +4. Okay. Just check my calculation once. And for this one, x equal to 2, the value of y will become 3 into 2 minus 2 cube plus 2. So that's becoming 6 minus 8 plus 2. So interestingly, that's becoming 0. Okay. So that's now showing me a very interesting pattern of this graph. It's showing me that this graph is something like this. Now I can get a reasonably, I won't say 100% accurate graph, but I can get a reasonably good shape of the graph because I have a lot of data with me. Okay. I'm understanding that the function is going something like this. Starting from a value of +4 when x is -2, and it's dipping all the way to y equal to 0 at the point x equal to -1. Then it's increasing all the way to 4 at x equal to 1, and then it's coming to 0 at x equal to 2. So in the limited domain, I will make the graph only up to this point, but actually this graph would go further also. And also I can see that in between over here, that at x equal to 0, what is the value of y going to be? So it's going to be 2. So I know that my y-axis has to be somewhere here. So at 0, it's cutting the y-axis at the point 2, whereas this point is the point of local maxima, where its value is becoming 4. And interestingly, I should cut this short a little here because at this point also, interestingly, naturally the function would go like this, but I'm making it only in the limited domain. So at -2 it is like this, at -1 it is like this, at 1 it's like this, and then again at 2 it is like this. So it has this kind of a shape. So this function, which was y is equal to 3x minus x cube plus 2, but for the restricted domain that I've taken, x is belonging only to -2 to +2. I can see that the range is also becoming restricted to between 0 and 2. Okay, so it has global maxima equal to 2 and global minima equal to 0. But in addition to that, it also has 1 point of local minima, where x is equal to -1, y is equal to 0, and 1 point of local maxima, where x is equal to 1 and y is equal to 4.
So
Oh, sorry, this is 4. My mistake. Yeah, these values are also 4. This is what you are pointing out.
yes, sir.
This is 4. Okay, so you can see that just by using that simple concept of rate of change telling me whether the function is increasing or decreasing, and add to that the concept of peak point and dip point, that is local maxima and local minima, and the concept of domain and range, I'm actually getting quite a nice set of tools to analyze the graph of a function, which is otherwise reasonably complicated because it has a term 3x and minus x cubed, which are kind of competing with each other. 3x is trying to take the value of y to positive values when x is positive and negative values when x is negative. Whereas on the other hand, the competing factor minus x cubed is taking y to negative values when x is positive and positive values when x is negative. So as they compete, they at different places, the different terms dominate, and according to that, the graph of the function has this behavior. So this is like the great scope that differential calculus has in helping us analyze the behavior of functions, the special points in the graph of the function, like local maxima and minima, and also the overall range of the function for a given domain. Okay, people, so I have another lecture coming up, so we will conclude the session here today.
Sir, like
Yeah.
my doubt.
Yeah, I will pick up your doubts in the next lecture. Also, we have some doubt sessions coming up. So, okay, I will try to send you some hints for the doubts. You can just drop me a WhatsApp message also. Plus, you have some doubt sessions coming up, and if the doubts are not cleared by then, I will definitely clear it in the next lecture because I will be doing some questions based on the worksheets also in the next lecture. All right?
Okay, sir.
Okay.
Thank you.
So will we be getting a practice worksheet for this?
Yes. Today's assignment will be based on behavior of the function, including local maxima and minima concepts, plus some revision questions again on chain rule and all that, but mostly based on the newer concepts.
And sir, can you send the class notes also?
Yes, I will send the class notes and the lecture recording also. Don't worry. Okay.
Sir,
Yes.
we were point for taking the module books. Sir, but I have.
Heth, I'm not able to hear you, Beta. Can you speak a little louder?
Yes, I guess we were being called to the Northern School to take our books, module books. Sir, but I have, sir, means it has all that chapters which are being taught now, the vectors, calculus, kinematics.
Yeah.
Sir, that is only the book now which is being.
Yeah. The one that you have the PDF of already, no? You must be having the PDF module 1 in physics, chemistry, and maths.
Yes, sir, I have both the PDF and the book. So
yeah, so that same one only. Yeah, that's correct. Abhi tak only module 1 has come, okay?
Okay, sir.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay, people. Bye. Have a nice day. Yeah.
Thank you.
sir.